Hello and welcome to the Feature Engineering Case Study in Python. I'm Mike West and I'll be your instructor for this course. On average, we Earthlings create 2.5 quintillion bytes of data every single day. In the real world, you need to have the ability to harness all that data and extract value and signal from that messy data. This course is going to give you a toolkit needed to go over that data with a fine-tooth comb to extract every last ounce of value in order to translate it into something incredibly powerful. More specifically, in the course, you're going to learn the basics of the end-to-end machine learning pipeline before delving into feature engineering. We're going to cover topics like exploratory data analysis, data cleansing, normalizing features, transforming features, and even creating new features from your data. You're going to cap off the course by evaluating different sets of features against one another on real machine learning problems in order to understand the value of each step we took in our feature engineering pipeline. Thank you for your interest in this course, Feature Engineering Case Study in Python. Now let's get started. Let's go over some assumptions about the background knowledge you're going to need for this course. This is going to help you get the most out of the course. Firstly, it's going to be helpful if you have some entry-level Python knowledge. Just some basics, mind you, like how it works and the core syntax. Additionally, how to install it. I'm not going to be showing you how to install Python. That should already be done. Beyond that, it's going to be helpful if you have some experience using NumPy, Pandas, and scikit-learn, as we're going to be relying on these heavily throughout the course. Some experience handling data and doing some basic data analysis or data manipulation would also be helpful, but it's not required. And lastly, we'll be focused on a very specific part of the machine learning pipeline. So having some familiarity with the foundation machine learning concepts is going to provide you some proper context for the part of the pipeline we're going to be focusing on. Now, it's okay if you don't know them inside and out. Throughout the course, we're going to review many of those machine learning foundations before we really dive into feature engineering. Before diving into the course, let's make sure you're set up with all the tools and software you need to follow along. In this course, we're going to be working with the Python version 3x fork. If you have a different version of Python, just be aware that certain codes in the exercise files may not run as you expect. We're also going to use the Jupyter notebooks and the Anaconda distribution of Python. Everything you need for the course, that's the Python 3x version, the Jupyter notebooks, and all the packages can be acquired very easily by installing the free Anaconda distribution. All right, now that we have our bases covered there, if you're doing your own exploration, you're going to want to install some additional Python packages from the Anaconda distribution. To do that, just follow the instructions to install the additional packages. Anaconda makes it very easy. From the command line or from the Anaconda prompt, just enter conda install, and then the name of the package you wish to install. Or if you want to install a specific version, use the same command, but just add equals in whatever version you want to install. An alternative is to use what's called a package manager called a pip. The syntax is exactly the same. You would just call pip instead of your package name. Either of these commands are going to work to install the packages you need. One last note, if you're having problems installing Anaconda, launching Jupyter notebooks, or installing packages, the Anaconda documentation is quite good. Those docs likely contain the solution to any problem you may be facing. All right, now you've got the tools you need. Let's start working through this course. Let's review the process of building a machine learning model at a high level. This is going to provide some context to understand the part of the process that we're going to be diving into in this course. It's important to note we're going to be talking here in general terms. This is what most machine learning pipelines look like, but there are so many variables in play that can impact the pipeline. So in this course, we're going to be talking about generalities. You're going to start with a full data set. This step in the process will be exploring data to really understand the type of features we have, what they look like, and how they relate to the target variable. We're going to be using some techniques that will clean the data and create some new features. This may sound simplistic, but it's probably the most critical phase of the entire pipeline, and this course will exclusively reside at this step in the pipeline. With that said, we're going to be running through the entire pipeline in the last chapter of this course to compare the performance of the models with different data sets and different features we've created and cleaned. Moving through the rest of the process, the next step is to split the data into training, validation, and testing sets in order to prepare the fit model and the evaluate on the end-scene data. Now we're going to be using five-fold cross-validation to explore a variety of different hyperparameter settings for each algorithm. In the last chapter, we're going to fold steps 3 and 4 into one step using Grid Search CV, which is a tool in scikit-learn. Now we're going to select a couple of our best models and evaluate them against each other on a validation set. Lastly, we're going to select the best model in the validation set performance, and we're going to evaluate it on the training set to get a completely unbiased view of what we can expect the model to perform on totally unseen data. You're going to run through all these steps in the final chapter, but you're going to live mostly in the first phase of this entire course. In conclusion, in this course, we're going to be focused on creating features. And then in the last chapter, you're going to build a model on top of those features. We're going to be using random forest models with a little hyperparameter tuning. If you're interested in learning more about the various models and algorithms like gradient boosting or logic regression, be patient. The XGB course is going to cover these in great detail. All right, in this lesson, let's cover a few basics of feature engineering. You might describe feature engineering as the process of transforming raw data into features that better represent the underlying signal to be fed to a machine learning model, resulting in improved model accuracy on unseen data. Again, we care about the model's ability to generalize to data it's never seen before. It's important to understand just how messy raw data is. There's a story in almost all data, and feature engineering is about teasing out that story. It's about taking the mess and funneling into or transforming it in some way to create something that is clean and understood by a machine learning model. For instance, you could tell me a story about a fraudulent credit card transaction that makes perfect sense to me, and I'd be able to recognize it as a transaction, whether it should be able to go through or not. Of course, it probably took you a couple minutes to tell me about it, and you told me about it after it had happened. The challenge is that no human being can review every single credit card transaction in real time. Luckily, automated algorithms or machine learning models can do that. So, the challenge here is taking the story that you told me about the fraudulent transaction and then representing that story cleanly in data for a machine learning model to pick up on. That's what this course is all about. We've previously looked at the machine learning pipeline, and it looked like a nice, clean, and linear process. The reality is it's a little less clean and less linear. What often happens is you'll pull the raw data, you'll explore that data, you'll clean it, you'll create new features, and then you'll fit the model on top of it. And maybe you'll evaluate your model and it's not that great. Then you go back and transform one of the features, then refit the model. And then maybe you'll evaluate the model again, and it's not so great again. Therefore, you go back and you transform one or more features. You then refit the model and evaluate it again to see if the new transformed features improve the model at all. Then maybe you circle back and drop a feature that doesn't appear to be providing any signal to the model. Then fit and evaluate it again. The reality is, most of the time, you really don't know how valuable a feature is until you test it in the model. This process is an iterative cycle and what the development of a machine learning model typically looks like in practice. Next up, we're going to dive a little bit into why feature engineering matters so much. Feature engineering may well be the unsung hero in machine learning. Massive amounts of data and state-of-the-art algorithms get attention, while feature engineering and data cleansing sit in the shadows. Without the data, these models are vaporware. In other words, you need to engineer features that allow the machine learning model to pick up on the signal in the data. There's a popular phrase that's applied to many of these processes that holds true in machine learning: garbage in and garbage out. A great manufacturing pipeline cannot cover up low-quality materials. A top-notch chef cannot overcome low-quality ingredients, and a state-of-the-art machine learning algorithm cannot cover up poor features. In other words, the quality of the information coming out of the process cannot be better than the quality of the information that went in. Let's put it another way. The quality of the features we feed the model is the primary limiting factor on the performance of that model. You can have a lot of data and an incredible algorithm, but with poorly defined features, your model is going to perform poorly. Better features help in several ways that may not be immediately obvious. First, they give us more flexibility. With great features, your algorithm choice and hyperparameter tuning becomes less important. You can select suboptimal algorithms and hyperparameters and still end up with a really good model. With poor features, you don't have that luxury. Another benefit is they allow more simple models. With great features, you don't need a super complex model to parse out every ounce of value in the features. With good features, even a simple model can be quite powerful. Complex state-of-the-art algorithms get the attention, but simple models are easier to understand, easier to debug, easier to optimize, and often run much faster than these state-of-the-art counterparts. When you're trying to run a model on something like a single credit card transaction, the ability to run the model, even in a couple milliseconds faster, is a huge win. Let's discuss some of the tools we have at our disposal for feature engineering. Let's start with something that, again, you won't read about often in academic papers or textbooks, and that's common sense. Many times, it's the most powerful tool we have. In other words, take a step back and think about the factors you would expect to influence whatever you're trying to predict. A very simple example is fraud detection. Maybe if it's a credit card used in a country that has never been used before, at a time of the day that it's never been used, then maybe that's more likely to be fraud. You should make sure those features are included in your model. On the other side of the coin, the date of the birth of the card holder is probably irrelevant to whatever fraudulent transaction you're trying to predict. Don't distract your model from things it should be focusing on. Get rid of irrelevant features. Given a set of features you think are relevant and helping the model pick out the signal in the data. You need to clean those features to make sure the model can actually use the signal. For instance, you can unmute missing values, you can remove outliers, so that the model doesn't go chasing data points that are not representative of the underlying trends in the data. By definition, outliers are not representative of trends, so get rid of them. Another way to clean your existing features is to use different scales. Think like measuring something in centimeters versus meters. It can be helpful to scale your data or normalize it, so your data and all your features are on the same scale. Lastly, similar to outliers, if you have skewed data, the model might go chasing the long tail of the distribution instead of focusing on the actual underlying trends in the data. You can transform skewed data to make it more compact, easily understood distribution. Another tool is combining two features into one, where one feature makes sense. Quality trumps quantity every single time when it comes to features. On the other side, maybe you have features that aren't really valuable. By using common sense and domain expertise, you may figure out that splitting a single feature into multiple features could actually uncover some value that the single feature did not capture. Sometimes converting a continuous variable into more simple categorical variables is also useful. For instance, if someone's applying for a loan, including a simple binary feature indicating whether they defaulted on a loan before might actually be useful to the model, rather than a continuous feature indicating how many loans the applicant has defaulted on. Lastly, you can learn new features from existing features. One area where it's done a lot is in text data. There are algorithms like Word2Vec that can help you learn different, more useful representations of the words. This can be powerful, particularly for natural language processing problems. Now, this isn't a complete tool set, but it can be useful for feature engineering, and it does cover the surface area and many of the things we're going to use throughout this course. For the entirety of this course, you're going to be using the Titanic dataset, which is a publicly available dataset that's commonly used for machine learning problems, and it was also a Kaggle competition. This dataset contains information about 891 people who were aboard the Titanic when it departed in 1912. Some people aboard the ship were more likely to survive than others. Your task is to build a model that's going to predict whether people are going to survive using the information about those 891 people on board. The features included in the dataset are as follows. You have the name of the passenger, ticket class, first, second, or third. You have the gender of the passenger, the age in years, number of siblings and spouses aboard, the number of parents and children aboard, their ticket number, the fare they paid, their cabin number, and the port they embarked from. And there are three possible values here. C equates to Cherbourg, Q equates to Queenstown, and S equates to Southampton. Now, even in that initial read-through, you've probably started to get a decent feel of the features that are probably going to be useful. At some point, that probably won't be. Let's start off by reading our data. We're going to import the data in pandas via a built-in method for reading CSVs. Now we're going to print the first 5 rows, so you can scan through all the columns. There are a couple things you might want to highlight here. Now, passenger ID seems like it was assigned based on the order purchased in their ticket or something to that effect. So it's unlikely the feature is going to play a role. It could also be a monotonically increasing key from a relational database, where the data was exported from. You also notice that this set features a mix of strings, name, or sex. Truly continuous features like fare or age, and some that may have a couple of different possible values like embarked and peak class or passenger class. Keep in mind that as we move through this course, as the type of feature it is, it's going to inform you how to handle those features. And lastly, you're going to notice the NaN values for the cabin. That means it's a missing value. As you're well aware of by now, NaN means not a number. Now, one of the first things you always do when you look at the new data is to check how many rows or columns you have, also known as observations. We can do this by easily calling the built-in shape function from pandas. So let's go ahead and call it the shape function. It tells us we have 891 rows and 12 columns for features. Another word for feature is attribute. Those three things are synonymous: columns, features, and attributes. Now, we've just noticed from looking at the first 5 rows of our data that we have different types of data here. Let's get more concrete by calling the Titanic dtypes to print out the data type for each feature. When we do that, you'll notice that we have 7 features that are either integers or floats. Then we have 5 features here that are objects or categorical. This is a good first step to understand the type of data, and it's going to help us frame the exploratory analysis of the data. Lastly, one other thing you should look at is the distribution of whatever we're trying to predict. In this case, we're trying to predict whether a given individual would survive or not. So you can look at the distribution of the outcome variable by calling that column, and then by calling the value counts attribute. You can see that 342 out of the 191 people aboard survived. So in machine learning terms, we can say that we have a semi-imbalanced target class, in the sense that it's not a 50-50 split. We have more zeros in our data than we have ones. In our example, about 38% of the rows are what we call positive cases, or the thing that we want to predict. It's not uncommon for that number to be less than 1% of our machine learning application. Think about fraud detection as an example. What percentage of real transactions do you actually think are fraudulent? Probably less than 1%. When you have this kind of class imbalance, that's the name given to this problem, it can be difficult to model or pick up the signal in those positive cases, because it's drowned out by the negative cases. In this scenario, you're going to want to make adjustments to the model so it can better pick up the signal in both the cases. Now, often the easiest and most common adjustment is to simply downsample the negative or majority class. With that said, our dataset is not terribly imbalanced, so we're just going to move forward without making any adjustments for now. Now that we have a basic feel of the data we're using, let's start exploring the features. Let's start with some basic exploratory data analysis on just the continuous features in our data. In this lesson, we're going to do some high-level exploration, and then in the next lesson, we're going to plot some of those continuous features. Let's get started by just reading in our data and printing out the first 5 rows. Now let's take a second and point a few things out. We do have personal identification information in here, like name, which we'd normally be really careful with, but this is public information. In the previous lesson, passenger ID is technically a numeric feature, but it's safe to assume that this is assigned randomly, or it's a monotonically increasing key, and in which case it's not needed, so we're going to drop it. In addition to dropping passenger ID, we have name, ticket, sex, cabin, and embarked. These are all non-numeric features. So we're going to go ahead and drop these for now, so we can focus on the continuous features for this lesson. Next up, we have a list of column names that we want to drop. In order to drop them, we just call our frame.drop. We're going to pass in our list of features we want to drop, and then we'll say we want to drop it along the axis equal to 1. And that just tells Python that we want to drop the columns, not the rows. And lastly, we're going to tell pandas to do this all in place. In other words, we want to alter the Titanic data frame as is. We don't want to create a new data frame. Let's go ahead and print the first 5 rows out. So now we can see we have a nice clean data set to work with. One useful thing to do with numeric data is to call describe method on it. We can use the built-in pandas function to get the shape of our data. So let's go ahead and do that by calling Titanic describe. You can see a couple of things here. You'll notice that the counts of age, we only see 714 values, even though we know there are 891 rows in our data. It's important to know that rows are often called observations in the applied machine learning space. All right, moving on. So this indicates that we have some missing values. We'll dig into this in a minute. Our target variable is survived and it's binary. Since it's binary, we can use the mean to tell us the percent of people that survived in this data set. The balance of classes matters for classification problems, both for the reasons that I already mentioned, and that the model has a hard time finding the signal on imbalanced data sets, but also from a valuation perspective. For instance, let's just say that 99% of the people in the data set survived. Then the model could simply predict that every single person would survive, and it would be right 99% of the time. But that's not a good model. That's not what we're looking for. So this class imbalance also gives you a perspective and a baseline of what a very naive model could achieve without learning anything from the data. Lastly, we can see that all the integer variables, that's p-class, sib_sp, and parch, all have a pretty limited range, which makes sense. P-class has a limited set of outcomes, and either first class, second class, or third class, and sib_sp, which is siblings and spouses aboard, and parch, which is parents and children aboard, are limited by, well, biology. It's going to be useful for us to keep this in mind as we move forward. These should not necessarily be treated as the same as features like fair and age. Now that we have a decent feel for the distribution, let's look at the correlation matrix. And here we're looking for a couple things. Actually, we're going to look for 2 things for each feature. The first is how correlated it is with the survived column. We want the absolute value of the correlation between the features and that thing you're trying to predict to be quite high. Keep in mind that a strong negative correlation is just as useful as a strong positive correlation. We just don't want the correlation to be close to 0. Secondly, we want to know how correlated a feature is with all the other features. We want the correlation with other features to be low. When the features are correlated with each feature, sometimes it can confuse the model because the model isn't quite able to parse out which feature the signal is coming from. So, in pandas again, we're going to make it very easy to create a correlation matrix. We're just going to call titanic.core. Now, let's take a look at that survive column. You can see that p-class and fair have the strongest correlation here. So that gives us an idea that those 2 features might be useful in making predictions. However, You'll also notice that fair and P-class have the strongest correlation between features. Remember, negative correlation is still a correlation. So as fair increases, P-class decreases, which makes sense. As you go from third class to second class to first class, fair is going to go up. Let's start with some basic exploratory data analysis on just the continuous features in our data. In this lesson, we're going to do some high-level exploration, and then in the next lesson, we're going to plot some of those continuous features. Let's get started by just reading in our data and printing out the first 5 rows. Now let's take a second and point a few things out. We do have personal identification information in here, like name, which would normally be really careful with, but this is public information. In the previous lesson, passenger ID is technically a numeric feature, but it's safe to assume that this is assigned randomly, or it's a monotonically increasing key, and in which case it's not needed, so we're going to drop it. In addition to dropping passenger ID, we have name, ticket, sex, cabin, and embarked. These are all non-numeric features. So we're going to go ahead and drop these for now, so we can focus on the continuous features for this lesson. Next up, we have a list of column names that we want to drop. In order to drop them, we just call our frame.drop. We're going to pass in our list of features we want to drop, and then we'll say we want to drop it along the axis equal to 1. And that just tells Python that we want to drop the columns, not the rows. And lastly, we're going to tell pandas to do this all in place. In other words, we want to alter the Titanic data frame as is. We don't want to create a new data frame. Let's go ahead and print the first 5 rows out. So now we can see we have a nice clean data set to work with. One useful thing to do with numeric data is to call describe method on it. We can use the built-in pandas function to get the shape of our data. So let's go ahead and do that by calling Titanic describe. You can see a couple of things here. You'll notice that the counts of age, we only see 714 values, even though we know there are 891 rows in our data. It's important to know that rows are often called observations in the applied machine learning space. All right, moving on. So this indicates that we have some missing values. We'll dig into this in a minute. Our target variable is survived and it's binary. Since it's binary, we can use the mean to tell us the percent of people that survived in this data set. The balance of classes matters for classification problems, both for the reasons that I already mentioned, and that the model has a hard time finding the signal on imbalanced data sets, but also from a valuation perspective. For instance, let's just say that 99% of the people in the data set survived. Then the model could simply predict that every single person would survive, and it would be right 99% of the time. But that's not a good model. That's not what we're looking for. So this class imbalance also gives you a perspective and a baseline of what a very naive model could achieve without learning anything from the data. Lastly, we can see that all the integer variables, that's p-class, sib_sp, and parch, all have a pretty limited range, which makes sense. P-class has a limited set of outcomes, and either first class, second class, or third class, and sib_sp, which is siblings and spouses aboard, and parch, which is parents and children aboard, are limited by, well, biology. It's going to be useful for us to keep this in mind as we move forward. These should not necessarily be treated as the same as features like fair and age. Now that we have a decent feel for the distribution, let's look at the correlation matrix. And here we're looking for a couple things. Actually, we're going to look for 2 things for each feature. The first is how correlated it is with the survived column. We want the absolute value of the correlation between the features and that thing you're trying to predict to be quite high. Keep in mind that a strong negative correlation is just as useful as a strong positive correlation. We just don't want the correlation to be close to 0. Secondly, we want to know how correlated a feature is with all the other features. We want the correlation with other features to be low. When the features are correlated with each feature, sometimes it can confuse the model because the model isn't quite able to parse out which feature the signal is coming from. So, in pandas again, we're going to make it very easy to create a correlation matrix. We're just going to call titanic.core. Now, let's take a look at that survive column. You can see that P-class and fair have the strongest correlation here. So that gives us an idea that those 2 features might be useful in making predictions. However, you'll also notice that fair and P-class have the strongest correlation between features. Remember, negative correlation is still a correlation. So as fair increases, P-class decreases, which makes sense. As you go from third class to second class to first class, fair is going to go up. Let's look at the average fair by different P-class levels. Let's do this by grouping passenger class and then describing fair. You can see that there's barely any overlap in the interquartile ranges. In other words, the 75th percentile for fair in the third class is barely higher than the 25th percentile in the fair class for second class. And the 75th percentile for second class is actually lower than the 25th percentile for first class. So that paints a pretty strong correlation that could confuse the model if both of those features are included. However, As mentioned before, you never really know for sure how the features are going to interact with the model until you actually test it. You looked at simple correlation between the survived column and the other features just to give us an idea of what features might be useful predictors. Let's look at another way to do that. Let's go ahead and group by two levels of the survived column and look at the distribution of each feature for people that survived and people that didn't survive. In addition to that, let's go ahead and run a t-test on the two distributions to see if the difference between them is statistically significant. In other words, this will give us a very strong indication of whether, for instance, fare was different for people that survived versus people that didn't survive. So we're going to craft a few functions here to run this analysis. So we're going to start with the describe continuous feature function. For each feature we pass in, we'll start by grouping by a survived column. Then we're going to call a feature we passed in. Then we'll ask the function to describe that feature. Then we'll call the t-test function. And this will split the features into two lists, one for people that survived and the other for people that didn't survive. Then we'll pass in the two lists into the t-test method from SciPy stats and indicate that we do not want to assume they have equal variance. All right, that's a lot packed in here. I would encourage you to take some time to really dig through the code and test it a little bit. In the interest of time, let's go ahead and move forward around the code. Let's create those functions. Then let's go ahead and use them to loop through all of our continuous features. One by one, we'll pass in those features into discrete continuous feature function. All right, let's examine age. This tells us the average age of the person that did not survive is 30.6. The average age of the person that did survive is 28.3. However, the median for people that did and did not survive is 28. So take some time to really dig through these, as we're going to set the basis for much of what we're going to do moving forward. But we want to likely highlight two features. First, fare certainly stands out as we can see a pretty significant difference between the means, the medians, and even the inner quarter ranges. Secondly, class stands out as there seems to be some difference, but keep in mind the correlation between fare and class. This illustrates how correlation can skew your interpretation. Keep these things in the back of your mind as we move forward. Speaking of keeping things in the back of your mind, recall that we noticed age had some missing values. Now, whenever you have missing values within a feature, we want to understand whether it's missing at random, as in maybe it was never reported for certain people, or it's missing in some systemic way. For instance, maybe they didn't ask the age of people in first class. This will give us insight into how we handle those missing values. If you make inappropriate assumptions, like assuming it's missing at random, you may miss some value. One way to determine this is to do what we did in the group by. This time we're going to group by whether age is missing or not. So we'll call the Titanic group by. And what we're going to do is group by the age feature. And then we're going to call the null method. And this null method will return true or false based on whether the age is missing or not. And what that'll do is return the mean value for each of the other features depending on whether the age is missing or not. And what we're looking for here is a significant difference in any of the features, depending on whether the age is missing or not. Just to reiterate here that true or false means whether age was missing or not. So true means it was missing and false means it was not missing. We notice that there does seem to be some splitting here. For instance, people without age reported were very less likely to survive, had a significantly higher class, fewer parents and children, and a lower fare. So we could theorize that age wasn't recorded for people in maybe the bowels of the ship that were traveling alone. All right, let's summarize this. Nothing really jumps out here that would require us to treat these missing values of any kind in a specific way. Keep in mind, though, because you'll see very different results for some missing values, you're going to want to find out these categorical features. Okay, now that we've done some very high-level exploration of the continuous features and learned a little bit about the features, like the fact that age is missing at random and that fare and class might be good indicators of whether somebody survived. In the next lesson, we're going to plot our continuous features, which is going to help us uncover some additional patterns in our data that weren't visible in this high-level overview. All right, now let's go ahead and plot our continuous features to learn a bit more about the distributions and the relationships to the target variable. Take note you're going to be importing Seaborn and Matplotlib as the primary plotting packages you're going to use for this lesson. By the way, these are the two most used in the applied space. All right, now let's read in our data, but instead of reading it all in, we're going to tell pandas what we want to read in by passing a list of continuous features. After we execute that, we really want to understand the shape of our features and how they relate to the target variable, which is survivorship. One of my favorite ways to do this with continuous features with a binary target variable is to plot overlaid histograms, where you can compare the distribution of certain variables, say age, for people that survived versus people that didn't survive. In the last video, we saw that the average for age for somebody who survived was 28.3, while the average for someone who didn't survive was 30.6. The medians were the same. Anytime you want to try to represent an entire distribution with a single number, you're losing a lot of information. So, instead of relying on the mean or median, let's look at the full distribution. Remember, the age and the fare were continuous features, while passenger class, sibling and spouses, and parents and children were more limited in the range. Let's focus on age and fare with the overlaid histograms. Then we're going to explore a different visualization on the other three features. The code basically just lives through the age and fare, and then it grabs all the non-missing values for each feature and assigns them to lists, one for those that survived and one for those that didn't. Next, we're going to plot both of those in an overlaid histogram. So let's go ahead and execute the code. Now in our example, green means they survived and pink means they did not survive. So what exactly are we looking at here? Well, previously we concluded, based on the averages, that there isn't much difference in age between the people that survived and the people that didn't. This plot confirms that. You can see the distribution of the age for people that survived versus those that didn't survive, and it's basically the same. Now, for the fare, we notice a drastic difference on the mean. 48 people that survived and 22 for those that didn't. Now we can overlay this histogram, and you can see it highlights the caution you have to take when you're looking with averages instead of the full distribution. Anything outside your first bin, you're going to see a likelihood of surviving versus not surviving is very similar. For instance, in the second bin, you can see there are roughly 70 people that survived. Then there's a green bar, and then 100 people that didn't survive. That's the pink bar. So the takeaway here is that just the fare can probably help us predict whether somebody survived. But it may not be quite as cut and dry as the averages indicated. The average is being impacted by some outliers. Now, let's turn our attention to passenger class, siblings and spouses, and parents and children. The way we're going to do this is to plot what's called a categorical plot from Seaborn. This is going to allow us to plot survival rate for each level of these features. This is going to make a lot more sense when we actually do it. So let's go ahead and start by looping through these three features. We're going to call this catplot function from Seaborn. All right, let's pass in our feature for each loop, then our y value, which will be survived, and then we pass in the Titanic dataset. Then it asks what kind of plot we want. And we're going to tell it we want a point plot. You can explore other types of categorical plots in Seaborn documentation. Now, one final thing here. Let's set our y-axis to be between 0 and 1, just to ensure we're comparing these features on the same axis. So again, what are we looking at here? The points represent the percent of people that survived each level of the input feature. So, for first-class passengers, maybe around 63 or 64% of the people survived. Then we take a look at second-class passengers. Maybe that number's around 45%. And then there are the vertical bars, which represent the error. If we have a lot of data for a given level, the vertical bar will be small, indicating we're quite confident. If we have limited data, the vertical bar will be large. So we can see some obvious trends here. First class is more likely to survive than second class, which is more likely to survive than third class. Additionally, in general, people with more siblings and spouses aboard are less likely to survive. Now, it seems like the siblings and spouses feature and the parents and children feature all have to do with family members aboard, right? It's siblings, spouses, parents, and children. And when you have that, you're less likely to survive. As we mentioned before, anytime we can condense features down, we should go ahead and do that. It just gives the model less things to look through. So let's explore combining the features into a single feature. So all we're going to do here is just call each of our features. So we're going to call sib_sp first. And then we're just going to add them together. So to do sib_sp plus, we're going to replace the names here for parents and children. And then we're going to store that in a new feature. And we're going to call it family count. Then let's go ahead and plot this with a categorical plot. Next, let's go ahead and replace x column with the family count. Now you can see this relationship is a little muddier than it was when the two features were treated separately. Survivorship actually seems to increase until you get to 3, and then it drops off drastically. Maybe creating an indicator of whether a person has 3 family members aboard, or fewer is a good option here. But I would just highlight again that common sense and critical thinking is a critical component to feature engineering. I would be cautious about building data or creating an indicator variable without sound logic for why that type of building or indicator makes sense. For example, why would 3 family members be such a strong cutoff point? This seems to be what the data is telling us. But we want our models to generalize. Is there a reason that having 3 family members would be a really strong cutoff point? Or is it simply an anomaly in our data? This is a good time to note that testing different sets of features is really the only way to be able to tease out the predictive power. Otherwise, we're just coming up with some untested hypotheses. For instance, it's possible that the two separate features will actually be better than a single feature, even though it kind of makes sense to condense them down into a single feature that just tracks family size. Beyond that, as a general rule, we do prefer simpler models with fewer features, but we're going to need to test this out. To see if keeping two features is worth the additional feature. Now let's take a look at some categorical features. We generally do this separately because we'll use different approaches to exploring continuous features than we will categorical features. As always, let's start by importing pandas and then reading our Titanic dataset into a data frame. And again, just to make the data look a little cleaner, let's go ahead and drop all the continuous features that we already explored. Now we're all set and we're going to start exploring our categorical features. One of the first things you always do when you're exploring data is to look at whether there are any missing values, which we can look at using the describe method for continuous features. Now we can do this by calling our data frame, calling the isNull method we've already seen, and then we're going to call sum on the isNull. Again, isNull will return a Boolean, and then the sum method is going to sum up all the true values. So you can see here that there's a lot of missing values for cabin. About 75% of all passengers have cabin missing, and then there's a couple in Embarked as well. Let's put those on the back burner for just a moment. We'll dig into those in a few minutes. Another useful thing to do when you're looking at categorical features is to see how many unique values there are. The reason for this is you're going to treat a feature with only two values in the data set, for example, like sex, and a feature that has many like values very differently. So let's go ahead and loop through our column names, and we're going to print out the number of unique values for each column. So of course, you already know that there are two unique values for survived. But for the rest of the features, we can probably break them down into groups. The first group has very few unique features. So that would include sex and the port of the passenger embarked from. And the second group has some unique values also. That would be name, ticket, and cabin. So let's go ahead and treat those separately, and let's start with sex and embarked. An easy way to see the relationship with the target variable is to group by each feature, and then just take a look at the average value for the target variable. Again, since the target is ones and zeros, taking the average field will just tell you the percent of rows there are for one, or the percent of passengers that are grouped that survived. So let's do sex first. So let's go ahead and call dataframe.groupBy, pass in the sex feature, and then we're going to call the mean. Again, because survive is the only numeric feature in our data, when you call .mean, Python knows just to return the average of the survived column. So what this tells us is that 74% of all females survived, while only 18% of all males survived. That's not so good for the men, is it? This seems like there could be a really strong feature in our model. All right, now let's do the same thing for the embarked feature. So we're just going to copy the code down, and we're going to replace sex with embarked. So now you can see the port encoded as C has a slightly higher survival rate than the other two. However, it's pretty close, and certainly too close to be sure there's any real value here. Okay, let's go ahead and move on to the features with a lot of unique values. And we're going to start looking at the missing values that we saw in the cabin feature. If you recall, when we were looking at missing values for the age feature, we looked at the correlation between missing that to this feature. All right, let's go ahead and look at the relationship to the survived column. All right, so again, we're going to start with the group by, and then we're going to pass in the Titanic cabin feature. And we'll call the isNull again, and then we're going to call the mean. Again, what this is going to do, it's going to group by whether the cabin feature is missing or not. And then it's going to tell us for each of these two groups what percent of passengers in each group survived. So as you can tell, this is a really dramatic split. This says that over 66% of the people who had non-missing cabin values survived, while less than 30% of those who had missing cabin values survived. Again, when we looked at age, we're trying to determine if a missing value means anything. And so far we have found that it doesn't. But in this case, whether cabin is missing is a very strong indicator of whether somebody would survive or not. Now, this really illustrates the value of exploring your data. Typically, if you see a field that has a missing value for 687 out of 891 rows, you're probably just going to drop the entire column because it's not going to offer you a lot of value. However, for this feature, our exploration uncovered a tremendous source of value for the model. One hypothesis might be that people with an assigned cabin literally don't have a cabin and may be stuck in the bowels of the ship. and that's why so few survived. But ultimately, the reason doesn't matter so much as our treatment of the feature. In this case, a missing value for cabin means something. So when we get to the modeling phase, we're going to define an indicator variable to indicate whether a passenger had a cabin or not. You'll also notice that each cabin has a number preceded by a single letter. We could surmise that the letter represents the deck, and then we could add that one as another feature. But I'm going to leave that up to you to explore on your own. The next feature we want to look at is ticket. Recall, you previously saw that there were 681 unique values. Whenever you have 681 unique values for categorical variables in a dataset with 891 rows, it's going to be pretty challenging for a model to find any signal there, if any signal even exists. Let's take a quick look at the value counts to see if there are any frequently used ticket numbers that would appear to mean anything. So let's go ahead and call the Titanic. We're going to call the ticket column, and then we're going to call the same value counts method. We don't really see anything jumping out here. We do have a few numbers that appear 6 or 7 times, but they don't really seem to mean anything. So ticket appears to be assigned at random, so we're likely going to drop that feature. The last feature we're going to have to explore is name. Now, name itself shouldn't really have any influence on whether a person survived or not. However, if you look at the field, there are a lot of titles included. Now, the titles might provide you with a signal, as it might imply status, which could be correlated with the likelihood of them surviving. So let's go ahead and try to parse out the title. We're going to start by calling our data frame, and then we're going to use the name column, and then we're going to apply a lambda function to it. All right, the next thing we're going to do is to say pass in the name, split on the comma, which will split the first and last name, and we're going to select the first name and then split on that period. What we're going to split on the period is it ends the title for every name. So then we're going to grab the first token, and that's going to get us our title. The last thing you're going to do, you're going to include the .strip method, and that'll just remove any leading trailing white spaces. So now let's go ahead and store that as a new feature called title. Lastly, let's print out the first 5 rows. Now we can see that it returns titles like Mr. and Mrs. and Mrs. Now let's go ahead and look at a full list. And while we do that, let's go ahead and look at the percentage of people for each title that survived. The way we're going to do this is to create a pivot table. And then next, you're going to say that survived is a column that you care about. And then you want to group the data by title and sex because we know the title and sex are going to be correlated. Next, we count all the passengers in each title, sex segment, and also calculate the average number of passengers that survive for that segment. All right, let's go ahead and run this. You can ignore most of the titles with less than 10 counts, and that's why we included the count. For the rest, you can see they mostly align with takeaways that we saw with gender, but it's slightly more granular. You can see the outlier here is master, where it's primarily a male, and they survived at a 57% rate. Now in the next lesson, we're going to explore plotting these features. Next, let's go ahead and plot some categorical features to learn a little bit more about the relationship to the target variable. We just did this with our continuous features. Instead of reading in all the data, let's tell pandas just to read in the categorical features by passing in a list of those features. Take note that we're also going to omit the ticket feature since we found it wasn't useful in the last video. Now we really want to understand the relationship between the different levels of the 4 categorical features and the survival rate. We started exploring in the last video. This is just going to provide us with another angle to look at to get a feel for which features are useful and which ones are not. Let's start with our title feature. We're going to grab the name and then we're going to split on the comma. And then we're going to grab the first and last name. Then we'll split on the period. And then we'll just grab the title. And then lastly, we're going to call the strip method on the title to remove any leading or trailing white space. Now, only for the purpose of plotting, we're going to store this as title raw. The reason that we're going to do that is that we're going to take the title raw and we're going to group all the infrequent titles together into one group, just so that the visualization or the plot's a little more clear. All right, so let's go ahead and call title raw, and let's go ahead and apply the lambda function again. And then we'll say return x as long as x is a list of the most frequent titles. So we have master, Mrs., Mr., and Mrs. And then we're going to say, if it's not in that list, just group it under another one. And then we're going to store that as title. Next thing we're going to do is create a cabin indicator. We're going to use the handy numpy method, which just carries out the if-then logic. So we'll say if the cabin is null, then return 0, else return 1. Now we're going to use the same categorical plots that we used previously. This is the exact same code that we walked through before, but just as a reminder, we're going to loop through all the categorical features. We're going to create a categorical plot using the feature, using the survived as the y-axis, using the Titanic dataset, and then we want that to be a point plot. Then you're also going to want the x-axis to be between 0 and 1 to evaluate these on the same axis. And we've done this before. As a reminder, each plot indicates the survival rate for everybody in that group. And then the vertical bar is the error bar. The survival rate for people with the Mr. title is around 18%. The survival rate for anyone with the Mrs. title is around 80%. So this first plot shows us what we saw previously. Mrs., Miss, and Master have really high survival rates, and Mr. has a really low survival rate. And again, this is pretty close to the correlated gender. So now we're going to move on to the gender feature. More than 70% of the women survived, while only 20% of the men survived. So this feature has very clear splitting power here. Moving on to the cabin feature. This says that people without cabins had about a 30% survival rate, and those that did have a cabin were at around 66%, which again we already knew from our prior analysis. You could consider even just the last two features alone. They have a lot of power. Just based on the cabin indicator and gender of the passenger, you can imagine being able to get a really good idea of whether someone was likely to survive or not. Again, this is the value of data exploration. Now this embarked feature has to do with where they boarded the Titanic. C is Cherbourg, Q is Queenstown, and S is Southampton. Now we see some separation here, but you can also see that the vertical bars for Cherbourg and Queenstown overlap. This is where we need to apply a little more critical thinking. It's unlikely that where they boarded caused them to survive or not. More than likely, this is correlated to the other features that I've already accounted for in the data. For example, perhaps a higher ratio of men boarded in Southampton, or maybe Cherbourg is a more wealthy area than the other two, and so many people end up having these cabins. We can actually explore these hypotheses using a pivot table. So let's go ahead and call the Titanic pivot table. We'll say we want to look at just the survived column. We can make the cabin indicator for the index of the road labels, and then make embark the columns across the top. And then we'll just tell it we want the aggregate function to be count. The default for this aggregate function is mean, but we just want to see the distribution. Our hypothesis here is that more people that boarded in Cherbourg had cabins relative to the number of people that boarded in Queenstown or Southampton. And we can see here that in Queenstown and Southampton, there's drastically more people without cabins than with cabins. 15 times more in Queenstown and about 3.5 more in Southampton. Then we look at Cherbourg and it's relatively close. Only about 50% of the people had no cabin compared to the people that did have a cabin. Given that we know that people that had cabins were more likely to survive, this would explain why Cherbourg had a higher survival rate. We've learned that the title, cabin indicator, and sex have a very strong correlation with survival. It could be really useful. We also learned that Embark does not really provide much information for us, and it's already been covered by other features in the model. Therefore, it's probably repetitive and not useful at all for us. We're going to consolidate all the learnings and the takeaways in the next video. We want to count all the passengers in each title, sex segment, and also calculate the average number of passengers that survive for each segment. And you can mostly ignore most of the titles with less than 10 counts. That's why we included the count. And for the rest, you can see they mostly align with the takeaways we saw with gender. But this is slightly more granular. You can see that the outlier here is Master, where it's primarily male, and they survived at a 57% rate. Now in the next lesson, we're going to explore plotting these features. All right, let's summarize some of the key takeaways for each of the 10 features before we work on cleaning the data and then finalizing those features. We learned that the name on its own isn't very valuable. Someone's name probably didn't determine whether they were likely going to survive or not. However, the title is stored as part of the name, and that might be a proxy for status. And that likely is related to whether the person would survive or not. So, we decided the title is likely a more useful feature than name. The next three features, passenger class, sex, and age, remain as they were in the data. Now, recall sex is correlated with title, and fare is correlated with passenger class. That's something useful to keep in mind as you move forward. And as you're following along, it might be worth exploring using just one of those correlated features instead of both. We realized the next two features, that is the number of siblings and spouses aboard, and the number of parents and children, were very similar. So we decided to combine those into one feature that represented the number of immediate family members a passenger had on board. We'll need to test this a little more to see if that single feature is better than two features individually. We validated that ticket number was more or less random, which means there's not really any signal in that feature. We decided to use fare as it is, but again, keep in mind, it's correlated with passenger class. For the cabin feature, we noticed that the cabin was missing more than 75% of the passengers. We could have assumed it was missing at random, and in that case, we probably could have just dropped that feature because it wouldn't be providing much value to us. However, we did uncover the fact that there was a strong correlation between whether the cabin was missing and survival rate. So we converted this feature from a categorical feature with likely very little value to simply a binary indicator that seems to be a very powerful predictor of whether the passenger survived. This feature, more than any, illustrates the value of the process of feature engineering. While we did notice a correlation between the port from which the passenger embarked and their likelihood of surviving, we concluded that it's likely a causal factor. It is likely correlated with some other feature, and that feature is probably the driving factor here. Now, these are our key takeaways. We're going to be keeping these raw features because later on in the course, we're going to fit a model on the raw features to serve as a baseline to understand how all this works together to improve model performance. Recall that previously we mentioned that exploratory data analysis will decide our cleaning approach. Well, in this lesson, we're going to take what we've learned in the last lesson and implement some of those necessary cleaning steps. Specifically, we're going to start out with missing values. In machine learning, the technical term for replacing missing values is called immutation. There are three common ways of addressing missing values. You can either fill the missing values with a median or mean value of that feature, or you could build a model using the feature as your target variable and actually try to predict what a reasonable value would be given for all the other features. Or you can simply assign them a default value. And it's worth noting that this only applies to missing values that appear at random. Anytime you have missing values that don't appear at random, you should use the pattern in the missing values to your advantage, like we'll be doing for the cabin feature, rather than just filling them in with one of the three methods. One note before we go on, I mentioned previously that we're going to start to fit the baseline model on the raw features in the final lesson to see how much value we get from cleaning our data. For that reason, as we clean the features, we're going to create new columns in our data frame for the cleaned versions of the features. That way, we're going to keep all the raw features as they are. Let's start by reading in our data, and let's just get a quick reminder of where these missing values are. We can see that we have missing values in age, cabin, and embarked. Let's set aside cabin for now. We're going to address that a little later, as the feature is not missing at random. In this lesson, let's focus on filling missing values for age and embarked. Recall that we previously checked to see if the missing age values were correlated with any other feature, and if that actually meant anything, or is it something at random? All right, as a refresher, let's go ahead and run the first line of code again to highlight the fact that there are some differences, but probably not enough to conclude that this just isn't missing at random. So we're going to treat these as missing at random. And then we're going to use one of the most naive but most useful methods for filling missing values. And that's replacing the missing values with the average value for that feature. This way, it satisfies the model by making sure we have a value in there, but by replacing it with the average value, it's not biasing the model towards one outcome or another, because the age value will just be the average it will rely on with the other features and try to investigate whether a given person survived or not. Okay, let's actually implement this. So let's call Titanic, and we're going to call the age feature, and then we're going to use fill in a method. And then we're going to need to tell it what to fill those missing values with. So again, we're going to call Titanic, age, and then we're going to call the mean. When we're calling the age column, we're telling everyone to fill the missing values, and we want the missing values with the average value of that age column, and we're going to store as age clean. Then we can just double check that the missing values are replaced by re-executing the is null. So now you can see that the age feature still has some missing values, but the clean age feature is not missing any values. All right, let's go ahead and observe our data one more time. Let's go ahead and print out the first 10 rows. So now we can see the age clean column, and you can see that all these are integers. But then all of a sudden we have a float there. That's clearly an average value that was inserted for a missing value for the passenger. Since Embarked is a categorical feature with possible values of C, Q, and S, we're just going to add another value to indicate whether a value is missing. Then we can use the exact same code we used before with the fill in a method, and then we're going to store that as Embarked clean. Then we're going to print out the missing values for the columns again. Once again, you can see the raw Embarked column, we still have two missing values. But now with the clean column, we don't have any missing values. The last thing we're going to do is save our data. One thing we need to do before we write all this out to Python is not to write out the index. So we're going to say index false. Otherwise, if we do write out the index, then when we read it in later, pandas will think the index is actually a column in our data, and we don't want that. So we only want to write out the data that we actually care about. All right, we're going to write this out to a clean file called Titanic No Missing. In the next lesson, we're going to read in this data set for some further cleanup. All right, let's keep moving through cleaning our data. In this lesson, we're going to remove outliers in our data. Again, this is to make sure our model is fitting the actual trends in our data and not chasing down the outliers. Now typically, this is called capping to remove the outliers at the high end and flooring to remove the outliers at the low end. But in this case, we're going to just be capping our features because none of our features could have outliers at the low end. Let's start by reading our data that we saved from the previous lesson, and let's go ahead and describe on that. Now, it's worth noting that we're only looking for outliers in a one-dimensional space in this exercise. In other words, we know that fare and passenger class are correlated. As the passenger class goes down, fare goes up. So in this exercise, we could see that a passenger that had a fare of 50, and that would be high, but not high enough to be considered an outlier based on the distribution of the fare. However, if the fare of 50 was for third-class passengers, that would likely be an outlier in a two-dimensional space, as we would expect the third-class passengers to be on the low range of the distribution of fare. So that's an example of a data point that would be considered an outlier in a two-dimensional space, but it would not be in a one-dimensional space. And again, we're going to be focusing on just outliers in a one-dimensional space. We can see that the max values for fare and age might be a little extreme, but the rest seem okay. But that's not really a thorough analysis. Let's get a little more concrete with this. So we know that passenger class cannot exceed 3, so we're simply going to ignore that feature for now. Let's go ahead and look at age, siblings and spouses, parents and children, and fare. For each of these, we're going to take a full distribution of values. And then we're going to set the thresholds to identify outliers that exceed those given thresholds. The thresholds we're going to set are going to start at the 95th percentile, 99th percentile, and 3 standard deviations above the mean is commonly used as a threshold to identify outliers. Now let's go ahead and define a function that's going to do that for us. Next, we're going to pass in the feature. We're going to extract the values from that data frame, and then we're going to calculate the mean and the standard deviation. Then we're going to look through each value for that feature. We'll calculate the z-score, which is the number of standard deviations above the mean. Then we're going to check to see if it's more than 3 standard deviations above the mean. And if it is, then we're going to assign it to a list of outliers. Then we're going to print out the results. So let's go ahead and execute the function. Then we're going to loop through the 4 features that we're interested in and pass each of those features into our detect outlier function. Now you can experiment with testing different thresholds. There's not necessarily a wrong or a right answer here. Now just looking at the results at a high level here, since there's not too many really extreme outliers, I'm just going to go with the 99th percentile to cap out the top 5 or 10 most extreme values. With that said, from what we saw in the describe, we can see that the max for siblings and spouses and parents and children are 8 and 6, which is reasonable. So there's probably no good reason to cap them out at 4 or 5. So let's just leave those alone, and we'll cap out age and fare. So again, what we're going to be doing on this age clean column, and we'll just call this nice clip method, which will just cap that feature. And then we're going to tell it what we want to set the upper boundary equal to on the age clean feature. And then we're going to grab that quantile in the 99th percent, and then we're going to tell it to do in place. Basically what we're saying is, let's set an upper boundary equal to whatever the 99th percentile of this feature is. And then we're going to do that in place. And that means don't create a new data frame or a feature. And then we're going to do the same thing to fare, so that we can copy this all down here, and we're just going to replace age clean with fare. Now the difference here is because the fare is a raw feature unlike age clean, we do not actually want to create a new feature here. So let's copy it here, and we're going to set this whole thing equal to fare clean. So let's go ahead and run that and then describe on our data again, just to make sure that it did what we expected. So now we can peruse the uncleaned age feature and compare it to the age clean feature. And we can clearly see it's been capped. The next thing we want to do is look at the uncleaned fare features and compare it to the cap version. And you can see that our capping did what we expected. Lastly, we're going to write out our data to our data set called Titanic Cap. And don't forget the index false argument. In the next lesson, we're going to pick up on this data set, and we're going to work on transforming skewed features. In the previous lesson, we talked about removing outliers, so the model won't go chasing them, and then we can focus on the trends in the data. Now let's move on to a related topic, and that's transforming skewed features. Recall that we previously learned that skewed data can be problematic because the model will go chasing the long tail, instead of focusing on where the bulk of the data is. Removing outliers can shorten the tail by removing extreme values. But transforming your data can then change the shape of the distribution altogether, making it more compact, easily understood distribution. All right, let's start by reading in our data and importing the packages that we're going to use. In addition to NumPy and Pandas, we're also going to import Matplotlib and Seaborn for our visualizations, and StatsModel and SciPy for our analysis. Let's start by looking at our 2 truly continuous features. They are age and fare. We're going to be using the clean version of each of them. Now to start, we need to see if either of them are skewed. We can do that by looking at a simple histogram for each. So we're going to loop through these two features, and then we're going to print out the simple histogram using Seaborn. You can see the age outside of the spike caused from filling in missing values with a mean of 28, and that's pretty well behaved. It's pretty compact without any really long tails. However, you'll see that fair is heavily concentrated around 40, but it has a very long tail. And you can see that capping our outliers did help a little bit. Previously, the tail extended way up to 500, so capping it brought the tail in a little bit, but it's still pretty long. All right, let's explore some potential transformations and try to pull that tail in. We want to make it more compact, well-behaved distribution. Let's start with a little more detail about what the transformation is. A transformation is a process that alters each data point in a certain feature in a systematic way that makes it cleaner to use. For instance, that could mean squaring each value, or taking the square root of each value in a given feature. We saw that the fair had a long tail. Then the distribution would aim to pull that tail in to make it a more compact distribution, so the model won't get distracted chasing that tail. The series of transformations we'll be working with is called a box-Cotts power transformation. These are common types of transformations. The base form of this type of transformation is y to the x power, where y is the value of the feature and x is the exponent of the power transformation to apply. So you'll notice the table shows some more common power transformations using exponents from -2 to +2. In our first line table, an exponent of -2 means that it translates y to a -2, which is the same as 1 over y squared. All right, so let's introduce an example here to make it a little more concrete. Let's just say the fare for a given passenger is 50, and that's 1 over y squared. Y is 50, so 50 squared is 2,500. Then 1 divided by 2,500 gives you 0.0004. The next transformation is just 1 over y, so that's just 1 over 50. And then the next one is 1 over the square root of 50, and so on. So this gives you an idea of how different power transformations alter the original value. Now in practice, the process is as follows. Firstly, you determine what range of exponent you want to test out. Then you apply each of these transformations to each value of a given feature. And then you use some criteria to determine which of those transformations yielded the best behaved data. In this lesson, we're going to be working with the following two criteria. The first is something called QQ plots. The details of this plot are outside the scope of this course, but basically a perfect distribution would mean all the plots in the point would end up in a straight line, from the bottom left to the top right. Secondly, we're going to be looking at a histogram with the normal distribution overlaid. With this, we want our histogram of actual data to approximate the curve that represents a normal distribution, given the mean and standard deviation of the actual data. I will note that there are some normality tests we could apply here, but those are fairly heavily influenced by the sample size, so I tend to avoid them. Let's start by looping through 0.5 up to 10, and we're going to apply an exponent of fair of 1 over that number, and then we'll plot it. So our first sample would be 0.5, which just gives us 2. So we would square each data point, and then the second value in that list is 1, so the exponent would be just 1 over 1. So it would be the raw values. Then it would be 1 over 2, so it would be the square root and so on. So let's go ahead and run our QQ plots. What we want to see here is that the blue dots line up with the red line. And you can see in our example for the case of y squared, that's not the case. For the raw values, it's still not the case. And then you get the square root of the raw values. And you can see that things are starting to get a little bit more well behaved. Maybe somewhere around the power transformations over 5 or 1 over 6 looks a bit better than our raw values or the squared values. This provides us with some idea of the distribution that we want to head for. So now we're moving to the histograms. Given the information from the QQ plots, let's reduce our range from 0.5 to 10, down to 3 to 7, since everything outside of that did not really seem reasonable. So next, let's go ahead and plot a histogram for each transformation here. But let's get a little more concrete than that by giving us something to compare a histogram to make sure it's well behaved. What we're going to do is we're going to take the mean and the standard deviation of the transformed data, and then we're going to use the constructed normal curve using that mean and standard deviation. And again, we want to shape up our histogram to approximate the shape of a normal curve. And as we execute that, and we scroll through these, again, you'll notice none of these are perfect. Probably any of them are a reasonable choice at this point. They're all better than the raw data. But let's just go with 1 over 5. You can see that the distribution is much more compact now. So now we don't have to worry about our model trying to chase down the values in the long tail. Let's go ahead and actually transform that data and store it as a feature in our data frame. So in order to create our transform feature, we're going to call a lambda function on the existing feature. And then we're going to tell it to apply an exponent of 1 over 5 for each value in fair clean, and then store it in fair clean. And now you can see that these are the raw values. And you can see the transform values, where you take each of these and apply an exponent of 1 over 5. Lastly, let's go ahead and write out our data. In the next lesson, we're going to start with this data, and then we're going to learn how to create some new feature from the existing text. In this lesson, you'll learn how to create one simple feature from text. Now, in the field of natural language process, you can actually learn the new feature from using text, like with Word2Vec. However, our problem doesn't really lend itself to that type of feature learning. Previously, we learned the name of the feature probably isn't useful at all. A person's name likely has no influence on whether they survived or not. Based on that, in many cases, people may just throw away this feature. However, we explored the feature, realized that we could parse out the person's title, and then use that for a model. So in this lesson, we're going to add a title feature to our data. Let's start by reading in our data that we wrote out in the last lesson. We're also going to create the feature using a lambda function. So let's start by calling the name column. Then we're going to tell it to apply the lambda function, and then that's going to pass in the name. We're first going to split on the comma in the name, and then we're going to grab the second element, which is index equal to 1. Let's go ahead and grab title, first name, and middle name, and then tell it to split on title, first name, and middle name on a period. You can see that every title ends in a period. Therefore, let's tell it to grab the first element, and that should return the title. Now we just need to append the dot strip method to remove any leading or trailing white spaces. Next, we're going to go ahead and assign that to title. Now let's go ahead and print out the first 5 rows. Alright, so now let's pause momentarily. You can see we have all our raw features, and we've cleaned the version of the age, embarked, and fair. And now we also have a transformed version of fair, and we also have the title feature. Our data is starting to take shape in preparation for modeling. Recall the reason we created the title feature. It seemed to be a strong indicator of whether someone survived. Next, we're going to use a pivot table to look at the correlation of the title and how likely a group was to survive. Again, this is heavily correlated with the sex feature, but the difference in survival rate between something like Mrs. and Mrs. and the inclusion of master gives the model a little better understanding of who that person was and their circumstances. Lastly, we're going to write out this data with our title feature added. In the next lesson, we're going to look at creating an indicator variable. Recall when we looked at the cabin feature previously? We saw that it was missing over 75% of the passengers. Now, it would have been easy to assume it was just a recording error. And because of that, the information was missing for so many passengers, it wouldn't have been terribly useful for the model. But we dug a little deeper and found a strong correlation between survival rate and whether the cabin feature is missing or not. Now, this could lead us to make many different hypotheses. But the important part is that we know that there's a value and that we want to make it noticeably clear to the model whether the passenger had a cabin number or not. We can do that by creating a simple binary indicator. Let's start by reading in our data. And then as a reminder, if you group by whether the cabin feature is missing or not, and then take the mean of the survived column, you'll see that under 30% of passengers whose cabin is missing survive, while 2/3 of the people who didn't have a cabin survived. That's significant. Next, let's capture the missingness as clearly as possible for the model. We've seen this before. Let's go ahead and use a method from NumPy. That's going to carry out our if-then logic. We're going to pass in the Titanic cabin, and then we're going to call isNull. So again, this will just return a Boolean of whether the cabin is missing or not. And we'll say that if it's missing, return a 0. If it's not missing, return a 1. And then we'll just store this new feature, and we'll call it cabin_id. This will just indicate whether they did have a cabin, which will show up as a 1 in the data, or that they did not have a cabin, which will show up as a 0. Okay, now that we've created that feature, let's print out the first 5 rows again. So now we can compare the cabin and the cabin indicator and see whenever the cabin's missing, there's a cabin indicator 0. Whenever it's not missing, it's a 1. So that means the model doesn't have to try to figure out what C85 means relative to C123, because the letters really don't mean anything to the model. Instead, now it can just focus on the signal we've passed to it, whether the cabin feature is missing or not. Lastly, let's just write out this data set with the cabin indicator added. And then in the next lesson, we'll pick up on this data and we'll combine existing features into a single new feature. Recall when we were plotting our continuous features, we noticed that features that indicate the number of siblings and spouses aboard had the same relationship to our target variable as the feature that indicates the number of parents and children aboard. It makes sense then that we can combine these two features into a single feature that indicates the number of immediate family members aboard. In this lesson, we're going to create that feature and store that data for modeling. Let's start by importing the packages that we're going to use and reading in our data. As a reminder of what the relationships look like for the two features, let's go ahead and create these categorical plots again. Okay, the general relationships here are the same, and that makes sense. If there are more people on board than you care about, you may be less likely to survive yourself because you're looking out for those other family members. Let's try to encode that takeaway into a single feature. So we'll just add these two features together by calling Titanic sib sp, and then we'll add that to the parents and children feature, and then we're going to store that as family count. Next, let's create the categorical plot for the family count feature. So let's copy down the code for the categorical plot, and then we'll just change the name of the feature that we're going to use. Recall that we noticed a big drop-off after a family count of 3. This story isn't perfectly clean here, but in the real world, the story is almost never perfectly clean. So now we're going to save this feature, and we're going to test it out in the modeling phase. It's rare that you know for sure whether a feature is going to be powerful or not. Keep in mind we're running through this pipeline in a very linear manner in this course, but it's often cyclical. So maybe you define this feature, you go to the modeling phase, and then you realize that the model easily picks up the patterns with two separate features. And then you just drop that feature and revert back to the original features. But that's why we're keeping all the features on our data set, just to give us options. Lastly, let's go ahead and write that data out to a new family count feature. And in the next lesson, you'll learn about converting categorical features to numeric features. Now comes one of the procedural steps that's required, but it's not terribly interesting. If you're at all familiar with natural language processing, you know that Python does not inherently know what a word represents. NLP is actually the process of teaching the computer to understand and analyze the human language. A machine learning model doesn't know the difference between male and female. In fact, a machine learning model doesn't even want to see those strings. It wants to see numbers so it can learn the relationship between those numbers and whatever it's trying to predict. It's worth noting the numbers do not necessarily indicate an order. It just gives Python the tools to use these features for fitting the model. So when you have categorical features like we have, you'll want to convert them to numeric features. One easy way to do that is called label encoding from scikit-learn. The function will basically learn all the distinct values that a given feature could have. So for sex, it could just be male or female in the data set. And then it would convert it to a number. So now maybe male is 1 and female is 0. So let's quickly tackle this. Start by importing the package that we need and then reading in our data. Now we're going to look through the data and pick out the feature that's not numeric. We can skip name and ticket, as we'll be dropping those features for the reasons we've already discussed. So beyond name and ticket, we have sex, cabin, and then we have embarked. We have embarked clean, and lastly we have title. So let's go ahead and loop through those 5 features, and we'll start by instantiating our label encoder, and then we'll store it as LE, so that we'll just create a new instance for each loop. Then we'll take the encoder, and we'll fit it, and then we'll use it to transform the data. And I'll walk you through this in a minute. And then we're going to pass in whatever feature we have. Lastly, we have to ensure that it's a string. And the reason we have to ensure it's a string is because the missing values for cabin, or actually any missing value, is a NaN value. And this actually indicates to Python that it's an integer. So this type of string, just make sure that Python treats it as a string. And then lastly, let's take our new transform feature and store it under the same name. So again, for sex, it will look through all the examples in our data, and it'll notice that there are only 2 distinct values, male and female. Then it's going to say, okay, I'm going to map male to 1 and female to 0. So within the transform step, we're taking the mapping and going through the data and converting male to 1 and every female to a 0. So create that loop, and then we're done. Let's print out the first 5 rows again. So now these features are prepared to be passed into a machine learning model and learn the relationships between these features and the target variable. Lastly, as always, we're going to write out our data. In the next lesson, actually in the next section, we're going to create the final data set we're going to be using for modeling. In this lesson, we're going to split up a full data set. We're going to use 60% of the examples in the training data set and 20% in the validation set, and then 20% in the test. We do this so that we can evaluate the performance of the model in the data it's never seen before. Now recall the very definition of machine learning. The entire goal for a machine learning model is to learn from examples and then generalize those learnings to unseen data. So splitting up our data will help us evaluate the model and the performance of the selection using unbiased results. Now let's go ahead and import the packages that we're going to use. We're going to use train test split from scikit-learn. This is going to make our job easier. So let's import that package and read our data in. So again, This is our complete data set with all our raw, clean, and created features. So the first thing we're going to do is split our data into features and then labels. And we get these features by dropping the survive column, in addition to the 3 features we identified as having no real impact on the outcome. So it's the randomly assigned passenger ID and ticket, and then passenger name. We'll go ahead and create this feature data set, and then we're going to need to assign the survive column to the data set labels that we're going to call train test split method. And the first thing we need to do is pass in our features, and then we'll pass in our labels. And the next thing we need to do is tell it what percentage of examples in the data set we want to allocate for the test set. Now, this is a good point to call out that ultimately, we want to split on features and labels into 3 separate data sets: training, validation, and testing. Unfortunately, the train test split method can only handle splitting one data into 2 sets. So we're going to be doing this. So what we're going to do is do 2 passes through the train test split method. On our first pass, we're going to tell it to allocate 40% of the data to the test set. And then we'll leave the 60% that we need for the training data set. And then we're going to run train test split again on that 40% and split it in half. So that would leave us with 60% of the training from our first pass, and 20% in the validation set, and 20% in the test set from our second pass. Additionally, you don't have to use 60-20-20 split. This is just a common used ratio. You could do an 80-10-10 if you wanted. So, focusing again on our first pass through, we've passed in our features, we've passed in our labels, we've told it to assign 40% to the test set. Lastly, we're going to pass in the random state, which is just the initialization seed for the randomizer. It's important to note that ordering the output has to be this way I've listed here. The train test split method is going to take the first features and split into 2, xtrain and xtest. And then it will take the labels and then split it on ytrain and ytest. So now that we have our first pass through setup, we're going to have our 60% in the training set and 40% in the test set. Now let's copy this down and do the second pass to the data to create our validation and our test sets. So what we're going to do is take the xtest and pass it through our features, and we'll likely take ytest and pass it through the labels. So we're going to take 40%, and now we're going to split that in half. Now we just need to rename the output from the second pass through train test split. We'll assign the first output to the validation set, so that'll make it xval and yval. And then the second part, we can leave as a test set. Lastly, let's just print out the first 5 rows of our training features. So one thing to note here is that the index jumps all over the place. Again, that's because the test split grabs samples at random to assign to the training and testing sets. And then it grabs the same index from our set of labels. So now let's quickly validate that this did what we thought it would do, and make sure 60% went to training set and that 20% to each test and validation set. What we're going to do here is we're going to loop through our training labels, validation, and test set. Next, we're going to take our original labels to the full data set, and we'll use that number of labels in the data set as a denominator, and then as a numerator we'll say how many examples are in the training and validation and test depending on the loop we're in. And then we can print that out. So we can see the first pass through the training data set represents 60% of the data. And then for the validation, it's 20%. And for test, it's also 20%. So that confirms we have 60% of our data in the training data set, 20% in the validation, and 20% in the test. Lastly, let's write all this to make sure that we are using the exact training, validation, and test for each model. So we're going to write our training, validation, and tests for our features, and then also for our labels. And remember, we're also telling pandas here not to write out the index. But even though we aren't writing out the index, pandas knows to keep the same order. So the first row in our training features will equate with some passengers as the first row in our training labels. Now, in the next lesson, we're going to explore standardizing our features. Recalling the lesson on tools that we have in our feature engineering toolbox, we talked about the features on different scales. It may be helpful to scale or normalize your data so all the features are on the same scale. We're going to explore that in this lesson. So let's go ahead and read in our data and then import this standard scaler that we're going to use to do our scaling. So you can see in our data that we have features clearly on different scales. For instance, fair and age are relatively big numbers, whereas cabin indicator is a 0 or 1, and embarked is a 0, 1, or 2. So what exactly does it mean to scale your data? It essentially means that you convert your data from raw numbers to numbers that represent how many standard deviations above or below the mean the value is. This is also known as a z-score. So for example, we previously learned that the average for the age was 29.7, and the standard deviation is 14.5. So let's say someone is 44 years old. Instead of the value in our data set being 44, it would be roughly 1, and that would represent the fact that 44 is one standard deviation above the mean in the age of this data set. Conversely, if someone was 15 years old, that would be represented roughly by a -1, meaning they were one standard deviation below the mean in the data set. Some machine learning models struggle with the data on different scales, like deep learning algorithms and some logistic regression problems. The actual algorithm we're using, random forest, does just fine with unscaled data. So we're going to be using the unscaled data in this course, but you should know how to scale your data. We're going to use the standard scaler tool from scikit-learn. So just like any other scikit-learn function, we'll start by instantiating this object, and we're going to do the default argument, so we won't pass anything into these parameters. And let's go ahead and store the scalar. Again, what happens when you're fitting the scalar is it's computing the mean and the standard deviation for each of the features in our training data. So now that we have our scalar fit, let's move on to the transformation. We need to tell the scalar the explicit columns we want to transform. So let's start by taking the column names in our data and then storing it as a list of features. And then we're actually going to do the transformation. So we're talking about our fit scalar, and we're transforming the training set, the validation set, and the test set. And then we're assigning them to data sets on the same name. So essentially, we're going to replace the original value with the scaled data. And just as a reminder, what it's doing here is for each feature, it's taking the mean and the standard deviation that it learned on the training data, and it's using it to transform each value for that feature in the training, validation, and testing sets. All right, so let's run through this transformation. Now you can see that these are all roughly on the same scale, where the numbers are representing the numbers of the standard deviations above or below the mean value for that given feature. Now that all our data is on the same scale, some algorithms will train more quickly, and some are going to even perform better. So this is a great skill to have in your toolbox. But because a random forest doesn't necessarily need scaled data, we're going to move forward with our unscaled features. We've already covered a lot in this course. Let's quickly refresh on the set of features that were there in our data set at the start of the course. We had the name of the passenger, ticket class, first, second, and third, the gender of the passenger, their age in years, the number of siblings and spouses aboard, the number of parents and children aboard, their ticket number, the passenger fare, their cabin number, and the port they embarked from. Now that we've done all the work of exploring this data, cleaning our features, transforming the features, and creating new features, it would be useful to understand the value work that we've done. In the final section of this course, we're going to take 4 different sets of features, build a model on each, and then compare their performance to understand the value of the work we've done throughout the course. So let's start by reading in our features. Now we're going to define 4 sets of features that we're going to use to build models on top of. Let's start with our raw original features. Now this will answer the question, what if we didn't touch our features at all, other than the required steps to converting categorical features to numeric? So this is just a set of features that contains all the original values we had in our data set when we started. Then we're going to define a set of cleaned original features. So this is just a set of original features with a minimum cleaning applied, like filling in missing values and capping and flooring. Then we'll define a set of features, and this is going to be the cleaned version of the original features, plus new features that were created. So that's cabin indicator, title, and family count. And then we're going to define a set of features called reduced features. And this is going to be a set of features that throughout our analysis, we found to be the most useful in predicting whether someone's going to survive or not. So that will be passenger class, sex, cleaned age, family count, transformed fare, cabin indicator, and title. With these set of 4 features, we can use the performance of our model on each to gauge the value of the cleansing, transforming, and creating features. Again, we're taking a very linear approach here, but normally we would circle back and iterate over and over again to find the best features. Lastly, let's write out this data by selecting each feature from the training, validation, and test sets, and then write those out to CSV files. Again, this will ensure we're using the same exact examples in the training, validation, and testing sets. We'll just be building models on different sets of features for each examples in our training, validation, and test sets. So starting on our first line here, what we're going to do is tell Pandas to select all our features in the raw original feature, and then write that out to a CSV called train features raw. Then we'll do that also for the validation and test sets. And we'll do this for each set of features that we want to define. So let's go back and run the cell that's going to create our feature sets, and then we'll write all that data out. Now to this point, we haven't touched our labels at all. However, we're going to be using them in the next section to train and evaluate our models. So let's move those labels over so that they're in the same directory as our features. Let's just copy down these training labels. So now we can go ahead and just write out these to the same final directory that we wrote our features out to. So now that we have all our data in place, In the next lesson and in the next section, we're going to build one model for each of the 4 features. Again, recall that features are basically the limiting factor on the performance of the model. So if we fit a model on each set of features and we compare the performance, that should give us a pretty good proxy for the quality of our features. Let's start by fitting our model on our raw original features to see how well the model is going to perform. First, we need to import our packages that we're going to use. We'll be using joblib to write out our fit models. We're going to use matplotlib and seaboard for some visualizations, numpy and pandas for some basic data manipulation. Then we're going to use the random forest classifier for our model. And lastly, we're going to use grid search CV. And again, this is just a wrapper around cross-validation that allows you to search for the best parameters for setting your model. Let's start by reading in all the original features and our labels for the training data. So here there are 8 original features that gave us the best off the bat, without any cleaning other than just converting the categorical features to numeric. So the first thing we're going to do is look at our correlation matrix to see if there's a strong pairwise correlation. And we're actually going to generate a heat map just to make it easier to visualize the correlation matrix. So as we already saw, Pandas makes it easy for us to generate your correlation matrix by just calling core on your data frame. So we're going to create our matrix here, and then we're going to pass into it the heat map. We also need to pass into it the matrix that we created from NumPy. And now you can see here that we have a correlation of 0.7 between passenger class and cabin. That most likely ties to missing values in cabin, because remember, we're not using that cabin indicator yet. Again, it's worth exploring on your own if you really want to drop cabin or passenger. It might actually result in a stronger model. Okay, let's get into fitting our actual model using grid search CV. With any model, it's useful to test some different parameter settings, as some data or sets of features will require more complicated models than other sets of features. And recall, we do care about the complexity of our model. Less complex models are actually one of the benefits of feature engineering. Pass grid search CV, a list of parameter settings, and then we'll run cross-validation with each of these settings to help decide which hyperparameters are best. So let's walk step by step through the process that we're going to use for each model in this lesson. I've created a function here that's just going to help us compare the results for each model. So grid search CV will store a result attribute, and that's what we're going to pass into the model. We'll tell that attribute to give us the best parameter settings, and then we'll print that out. And then we'll pull the average test score, which will just be the average test scores across the 5 folds, and then the standard deviation of the test scores. And then we'll print out those results for each hyperparameter setting. Then we're going to define a list of parameters as a dictionary. So you're going to be tuning 2 parameters for random forests: the number of estimators, which is just the number of individual trees, and the max depth of those trees. For any number of estimators, we'll use this comprehension to define our range that we want to explore. So we're doing this to the ith power for I in a range from 3 to 10. So with 2 to the 3rd power, that's going to be 8. And then we'll go 2 to the 4th, which is 16, and then 2 to the 5th, 32. You get the idea. The max depth we'll use 2, 4, 8, 16, 32, and none. Now, if we didn't set any of our own values for these hyperparameters, it would be 100 for the number of estimators and none for the max depth. In other words, each tree would go as deep as it needs. So now that we've actually instantiated our model and we've defined a range of parameters, now we can actually set up our grid search. So we're going to call grid search CV. We'll pass on our dictionary of parameters, and then we'll need to tell it how many folds we want to use. We said before we're going to use 5-fold cross-validation, which is the gold standard. And then we're going to store that as CV. Then just like any other scikit-learn object, we need to actually fit it. So we're going to call the fit function, and then we're going to pass in our training features and our training labels. Now, if we just pass in the train labels, scikit-learn will complain because this is a pandas column, and what it wants to see is an array. So we'll convert that to an array by calling values and .ravel. So now the last thing we want to do, once our grid search CV object is fit, so we want to pass into it the function that we've defined. So we can just call print results and pass in CV. So when we run this, what happens is it's going to pull the first item in the list for each parameter setting. So that would be 8 for the number of estimators and 2 for the max depth. It's going to run cross-validation, and then it's going to store the average accuracy and the standard deviation of the accuracy across the 5 folds. Then it's going to move on to the next hyperparameter combination and do the same. So by the end, each hyperparameter combination will have been run through the cross-validation to give us a pretty clean read on the best hyperparameter settings, given this set of data. So now that we can see that our best model on our data was about 512 estimators with a max depth of 8. This resulted in an average score of about 84.5%. So with these settings, we can move forward on the next set of data. Now we explored our features previously, so we have a pretty good feel for which features are useful for predicting whether somebody would survive. However, we also discussed that we're never really sure how each feature will impact the model. One great thing about random forest is it computes feature importance scores for each feature and how important it is for fitting the model. And one of the great things about Grid Search CV is it stores the best model as an attribute. So we can call CV Best Estimator and get access to all the attributes of that random forest model. So you can see we'll call feature underscore importances, store them as a feature IMP, and then we're going to plot all these out. So we can see that sex is by far the most important feature. That's not terribly surprising. Given the exploration we did, it's interesting to see that age was more important than passenger class. In our prior analysis, it looked like age wasn't really a strong indicator of whether the passenger would survive. Well, it looked like passenger class was a very strong indicator. Recall, though, we also mentioned that passenger class is highly correlated with both whether someone had a cabin and the fare they paid. So this might be a good example of the model getting a little confused between these features for what's really driving the relationship with the target variable. Recall that in cross-validation, within every loop, the model is only going to fit 80% of the training data. So once we pick out our best model, we should usually fit 100% of the training data. One of the great things about Grid Search CV is it actually does this automatically, and it stores the best model that was fit on 100% of the training data as an attribute called Best Estimator. So now this model is ready to be evaluated on a validation set, which we'll do later, once we fit our models. The last thing we want to do here is write our fit model out so we can use it later in this section to compare it against the other models on our validation set. JobLib allows us to pickle this model and write it out. Now that we've fit the model on raw features, let's fit the model on clean features. This will give us some insight into how much value in muting the missing values and removing the outliers provided for the model. Did it allow the model to better pick up on the underlying trends in the data? Let's find out. Let's start by importing the same packages we did in the previous lesson. Now we're going to read in the original clean features. So let's start the same way we did in the last video by looking at the correlation matrix. And this should look pretty much identical to the last video because we made minimal changes in the cleaning process. You can see the cabin is very highly correlated with passenger class. Again, probably because missing values were third-class passengers. We'll also notice that fare is highly correlated with passenger class, which makes sense. We have our function that's going to print out the best parameter settings for the data. And remember, some of the benefits of feature engineering include simpler models and more flexibility. So be on the lookout here of cleaner, better features resulted in the model with fewer or shallower trees. And this function will also print out the results of the hyperparameter settings, just like we saw in the previous lesson. Next, we're going to be exploring the exact same range of estimators and max step as we did in the last video. This code is the same code to the prior lessons. We have the same examples that we're training on, the same algorithm, and the same hyperparameter ranges. The only thing we're changing here is the features that the model is using. So we can see that the best hyperparameter settings for the model built on the clean features has a max depth of 8 and 256 estimators. That's a little bit more simpler than the model built on the original raw features. And now you can also see that the model has an 84.7% accuracy. Let's look at the feature importance for a random forest model stored in the best estimator. The results are nearly identical to the model on the raw features. That's not surprising, as what we did in our cleaning was try to clarify the picture for the model to see the underlying trends in the data, but we really didn't do anything drastic. Therefore, we shouldn't expect any massive change in performance. And the same is true with feature importance. We roughly see the same picture that we saw with our raw original features. The real test is going to be when we compare this model to the model built on raw features on the validation set. Lastly, let's write out the best estimator that was refit on the entire training data to a file indicating the model was built on the clean features. Now in the next lesson, we're going to build a model on all the features. Now that we fit our model on our raw features and our clean features, let's fit the model on all the features. And to be clear, when we say all, we mean the clean versions of the features, plus the new features we created. And this will give us some insight into how much failure the new features are providing us above what the simple features provided. As always, we're going to start with importing the same packages we did in the last lesson. And then we're going to tell pandas to read in the data set with all the features. So you'll notice all the clean features, plus our transformed features, our cabin indicator, our title, and our family count. Let's go ahead and take a look at the correlation matrix. Now, I just want you to know we're certainly breaking some rules here. For instance, we should not include both the fair feature and the transformed fair feature, since they represent the exact same thing. We just change one version to clean up the distribution. We also should not include the family count and the feature it was created from. We'll have a near-perfect correlation by keeping them both in the original version and the new version. And as you see with the family count, it has a 0.9 correlation with siblings and spouses, and a 0.8 with parents and children. You could also test out dropping those features on your own, just to see the impact of the final model performance. All right, let's move on to Grid Search CV. We have our function here that's going to print out the best parameter settings, as well as a full result of the combination of parameters. And just as a reminder, we'll be exploring the exact same range of estimators in the max depth as we did before. So we can see that the best model was the one with 64 estimators and a max depth of 8, resulting in an accuracy of 83.7%. This is a simpler model than we found with either the clean features or the raw original features. One thing to note here is that this is non-deterministic, so you could rerun the cells and get different results. And if you're running the code in the examples along with me, you'll likely have different results as well. Hopefully, by the end of this course, our takeaways will be exactly the same, even if the numbers are slightly different. So let's look at feature importance. Sex remains the most powerful predictor of whether someone's going to survive, but now we see the title moves into second place. So we can see this new feature we added is providing quite a bit of value, and maybe that's part of the reason why we're seeing a simpler model this time around. One more thing to note on correlation. We previously saw how powerful the cabin indicator was in splitting out the survived and those that did not. Yet it's one of the lowest features in the importance plot. This is likely due to its correlation to the original cabin feature. The model's not really sure what it should be attributing value to since they represent the same signal, even if the signal in the cabin indicator is a bit cleaner. Lastly, we're going to write out the best estimators that we found on our training data so that we can evaluate them on the validation dataset using our other models. Now, in the next lesson, we're going to build a model only on a subset of what appears to be the best features. We've explored our models on raw features, the clean features, and then all the features. Let's fit the model on the reduced set of what we seem to be the best features. How much signal can a small subset of features capture? Let's start by importing our packages and reading in our reduced feature set. And let's go ahead and run our correlation matrix again. Now, it shouldn't be much of a surprise that at this point, there's a reasonable correlation between passenger class and whether the passenger had a cabin, as well as whether the passenger had a cabin and their fare. How to handle this correlation in your features is something you'll have to get a feel for as you gain more experience. You could simply drop the feature or do something a little more complex, like using principal component analysis to generate features or components that are no longer correlated. For now, we're going to leave this alone. We're going to use the same function to print out the results, as well as search for the hyperparameter space, as we did in the previous lessons. Okay, we can see that the best model is the one with a max depth of 8 and only 8 estimators, and this resulted in an accuracy of 83.1%. It's easy to notice that 8 estimators is way fewer than we saw in the previous lessons. That highlights how the clarity and power of our features resulted in a simple model. Now let's look at feature importance again. This shouldn't come as much as a surprise either. Sex is clearly the most powerful feature, and we saw that across all of our models. We also see title being near the top consistently. We also transformed fair feature as being powerful in the model. Now, in the last step, before we compare all the models on the validation, let's write out the best model in the reduced set of features. In the next lesson, we're going to take all the models that we pickled and we saved, we're going to read them in, and then we're going to evaluate them on unseen data to find out which feature generated the best model. Up to this point, we've explored our data, done some feature engineering, fit models on the training data for 4 different sets of features, and we've saved the best model for each of these 4 sets of features. In this lesson, we're going to pick up on those 4 models and fit it on the training data set, and we're going to evaluate them against one another on a validation data set. This is going to give us a clear view of how the best models generated by each feature set will do on the data that they were not fit on. Keep in mind this is completely unseen data. Then we're going to select the best model based on the performance of the validation set and evaluate it on the holdout test set to get an unbiased view of how well the model will perform on the data that hasn't been used in any way in the model selection process. Let's start by importing the packages that we need, and I'll call out that we're importing accuracy, precision, and recall score calculations from scikit-learn.metrics. And then we're also importing a time package that's going to help us understand how long it's taken each of these models to make the predictions. Again, the latency of the model, or the time it takes to make predictions, is a critical component to all these models when you're scoring live data. And the simplicity of the model is one of the main drivers of that latency, and it often gets overlooked. So we'll be considering model latency when deciding the best model. Lastly, we're going to read in our features and our labels for our validation set. Now let's read in the models that we've stored. For simplicity, since they are all saved with similar naming templates, I'm going to read these in with the loop. And then we're going to store the model object in the dictionary. So the dictionary will have the model name as the key and the model object as the value. So we're going to loop through the raw original, the cleaned original, and all the reduced. And then we're going to load the model by calling joblid.load. Then we have to pass the location of these models. So we're going to have to go a couple levels to find them. Then go into the models dictionary, and then for each model, follow the names of the template so it can be loaded to the MLD raw original features and the MLD cleaned original features, and so on. Now we just need somewhere to store these models for each loop. So let's call this dictionary, and then we'll tell it we want the key to be the name of the model, and then we want that value to be the actual pickled model from what we're loading here. And lastly, we're just going to tell Python we want to pass into this bracket. So in the say.format, format, we're going to pass in a string that the MDL represents. So now we have all our data, and we have all those models stored in the model dictionary. All right, now we have a function called evaluate model that's going to help us evaluate these models on the validation and test set. And this function accepts the following arguments: the name of the model object itself, the features for either the validation or the test set, and the labels for either the validation or test set. Next, we're going to be using this time method that stores just the time when you run a given command. So between start and end, we're going to ask the model to make a prediction on all the examples in the validation or the test set. Next, we're going to store this time immediately before and immediately after those predictions were made. Then we're going to be able to calculate how long it took to make those predictions. Then when we compare model predictions and our model labels for accuracy, precision, and recall, we're going to print them all out together. And now we can just call the function for each set of features. We'll call evaluate model, and then we'll start with our raw features. Just the name of the features. Then we're going to call the raw model feature from our dictionary models. What we're going to say here is we want to run this on the validation feature set for the raw features and pass in the validation labels. And then for the clean features, we're going to do the same thing. We're going to pass in the name, pass in the model, pass in the original validation features, and the validation labels. Now previously we mentioned that these results are not deterministic in the training phase. This is true because training is not deterministic. In the training phase, if we run the cell twice, we could get two different results. However, now we're dealing with stored fit concrete models. So you can run the cell as many times as you want, and you'll get the exact same performance metrics. The latency will vary a little bit, but it shouldn't vary too much. All right, let's go ahead and dig into the results. You can see that the model built on all the features generates the best accuracy, the best precision, and the best recall. However, the model built on the reduced features generates the simplest model and the lowest latency. So how do we compare these things? Because now if you're just looking at accuracy for the reduced set of features, and it has the second best accuracy behind the models built on all the features, but it has a worse precision, and it has the second best recall. So this conundrum brings us to a discussion on how we balance these things out. How do we balance out precision and recall? And then how do we weigh the latency against performance? All right, so let's dig into this a little bit. The first is precision and recall trade-offs. Which model would you choose, or which metric would you favor when it comes down to the problem you're trying to solve on the business use case? For instance, the spam detector. Would you want to optimize for precision? In other words, if the model says it's spam, is it better to be spam, or else is it better to block real emails that people want to see? On the other side, if this is a fraud detection model, you're likely to want to optimize for recall, because missing one of those fraudulent transactions could cost you tens of thousands of dollars. All right, up next is the trade-off between overall accuracy and latency. It's a little bit easier in our case because the best performing model had the second best latency, and the model with the best latency was the second best performing model. So right off the bat, we can pretty much eliminate the models built on new features and clean features. But do we prefer the model built on all features that has a better performance with higher latency, or the model built on reduced features that isn't quite as powerful, but it's simpler? This comes down to a business use case. In a case like fraud detection, a couple milliseconds could make a huge difference. So it really depends on the use case. If we're going to deploy this in a real-time environment where the prediction speed is critical, we would probably want a small trade-off on the model performance, and we want to deploy the model built on reduced features because it's quite a bit faster. If model latency wasn't an issue or wasn't important to us, then we would go with a model built on all features because it generated the best performance. Since in our case, we don't have any prediction time requirements, we're going to go with the model built on all the features. So let's go ahead and evaluate on our test set. So the first thing we need to do is read the data in the test set containing all those features. That'll be the test features all.csv. Then we're going to store all those test features. Then let's call evaluate model. Then we're just going to copy it down where we evaluated on the validation set. And all we're going to have to do is change the features and the labels that we're passing in. Now, just as a reminder before we run this, you can see that performance aligns fairly closely with the validation set. The reason we evaluate on the validation set in the test set is because we use performance on the validation set to select our best model. So in a way, the validation set played a key role here in model selection process. So this test set was not used for any model selection. It's a completely unbiased view of how we expect the model to perform moving forward. Ideally, we're just looking for performance that is relatively close to what we saw in the validation set. We can see here that model performance is relatively close. Actually, it dropped a little bit. Latency went up a little bit, but it's still the best performing and the second best model latency. So now we've explored around 100 candidate models across 4 different features to try to find the best model for our Titanic dataset. We finally narrowed it down to this model built on all features with 64 estimators and a max depth of 8. We've robustly tested the model and evaluated it completely on unseen data. And we know it generated the accuracy of 83.7% on cross-validation, 83 on the validation set, and 81 on the test set. So now we have a great feel for the likely performance of this model with no data. We can be confident in proposing that this model is the best model for making predictions on whether the people aboard the Titanic would survive or not. The skills you learned in this course can be generalized to any new feature set and allow you to extract every last ounce of value out of the features in order to build the most powerful machine learning model.